And thanks, Elizabeth. I'm Tom Hanisco. I'm at NASA Goddard, and these are my coworkers, colleagues, working on the laser transmitter are Dimitrios Poulios, Paul Steisley, and Aaron Yevik. Data acquisition, signal processing are Steve Bailey and Reem Hanoun. Calibration and retrievals, Glenn Wolf and Julie Nicely. And optomechanical design is Andrew Swanson. And today I'll talk to you about a brand new IIT. This is an instrument concept, so it's a very low TRL. It's an idea that we'd like to prove, and it's called formaldehyde integrated path differential LiDAR. Next slide, please. The reason we're doing this is formaldehyde is important for air quality, and I'm just give you a very brief introduction to air quality. Ozone, nitrogen dioxide, and formaldehyde are the three main air quality gases measured from space by NASA, ESA, and other countries. Ozone is the smog that we really care about. It's produced from NO2, which is the oxidizer, and volatile organic compounds, which are the fuel. These VOCs are, propane, methane, anything that can burn. And they burn very slowly in the atmosphere, and they're oxidized by NO2, and they turn into ozone. The problem is we can't measure all the VOCs. But what we can do is measure formaldehyde, because it's produced from the degradation of these VOCs. So NASA and all the air quality institutions in the country are very interested in formaldehyde. Next slide. This is the challenge. The current method of measuring formaldehyde is passive. It's UV-vis spectroscopy. And in the figure on the right-hand side, I give a very oversimplified view of what passive sensing is. It's basically using the sun as a light source. The light from the sun reflects off the ground into a detector, but it also reflects off of all sorts of other things in the atmosphere, whether it's molecular scattering or scattering off of clouds. It still gets into the detector. So the path length of the scattering is ill-defined. It's not just from the top of the atmosphere to the ground and back. It has hundreds, if not thousands, of different pathways to get to the detector. And in order to retrieve the amount of formaldehyde in the atmosphere, you have to know the distribution of formaldehyde. And that's based on a modeled a priori. The problem is it's so highly uncertain that it's very hard to get formaldehyde right. If you have two different a prioris, you can get different answers for formaldehyde, as much as 40% difference. Active sensing, on the other hand, and I show that on the left, oversimplified, is basically a laser shine to the ground, reflected, and you do a Beer's law analysis. The problem with that is it's complicated technology, but ESTO, I'm hoping, will provide a solution. Next slide. Our solution is a concept. It's this integrated path differential LiDAR. And it's different than regular LiDARs in that we integrate all the way from the transmitter back to the receiver. We're not going to resolve any height information. It's not a profiler. It's just a simple Beer's law experiment. And I show that in the bottom right-hand figure. And it's the laser scanning over two rotational features in this case. The tunable laser scans over these features, and it gets specificity because only formaldehyde has this shape. The challenge in this method, besides the technology, is the low abundance of formaldehyde. But the mitigating factor is that formaldehyde science is what I call plus or minus 20% science. You only need to know formaldehyde roughly in order to do good science. You don't need this experiment to be perfect. You just need it to work. And so what we'll do is by showing this airplane on the left-hand side, we'll build a fiber laser at 1018 nanometers, triple it to 339, and transmit it And this will all be done on the ground. The airplane is just notional. And we'll obtain that spectrum that I show on the right when we receive the return signal. And when we fit this signal, we should have a measure of the formaldehyde in the atmosphere. Next slide, please. This is why our approach, I think, will work. And this is a little bit of spectroscopy. In this figure, I have a few different lines. The blue and the red lines are the formaldehyde spectrum at high resolution. So if you have an infinite resolved laser, you can scan these rotational lines. The black line is the integrated cross-section, or what you would see at half nanometer resolution. The point here is that if you can resolve these rotational lines, they're 5 to 10 times more sensitive than this integrated cross-section of formaldehyde. Passive sensors use half nanometer resolution. So we're about 5 to 10 times more sensitive to formaldehyde than a passive sensor using this kind of spectroscopy. The second thing I want to show is the blue and the red lines are measured at two different pressures. One at a low pressure, one at a high pressure, and the high pressure is pressure broadened. But you only see about a factor of 2 difference in these two extreme pressures. One is perhaps the stratosphere and one is the boundary layer. And this is important because with our IPDA technique, we're only sensitive to about a factor of 2 to changes in altitude. Whereas in passive measurements, the scattering weights will change by over an order of magnitude between the upper atmosphere and the lower atmosphere. So the significance is IPDA is 5 to 10 times more sensitive to formaldehyde, and 5 to 8 times less sensitive to the scattering and a priori than the passive sensing. Next slide. This is our proposed technology. So for this ICD, what we'd like to do is build a laser transmitter and test it on the ground. And it's in very simple terms, it's just an amplified fiber laser. So we use a tunable DFB or ECDL. That's an external cavity diode laser. And we amplify it up, and then we go through 2 harmonic stages to triple the output of this laser system. The output would be tunable with a narrow line width, so we'd be able to measure the rotational features of formaldehyde. It has enough power that we can get a return signal. Where the power is really important in this experiment, because if we hit a hard target, the return signal will be greatly diminished, especially in the UV, where the atmosphere scatters so strongly. I have a table just to summarize the parameters that we'll have. I do have a mistake in the table. It should be 20 microjoules, not 20 millijoules. But these are pretty reasonable values for a laser of this type. The real challenge is to push the wavelength of the system down to 1018. Systems can be built relatively easily at 1064 nanometers, 1016, even down to 1040. But it's a real challenge to push the laser down below 1020 nanometers. Next slide. We haven't started yet. We were going to start before this coronavirus hit us. I put in a blue box, and these are pretty hopeful that we can start in the fall. If not the fall, then early 2021. But what we'll do is we'll build and test our transmitter, and we'll do a ground demonstration. And what we'll do is we'll put a few in situ instruments along our ground path so that we can verify the concentrations. And then we'll work on the retrievals to optimize the retrievals to make sure we get the correct concentration of formaldehyde. This will be an 18-month project, and it's just a proof of concept. In the long term, what we'd like to do is move this to a movable platform, such as an airplane, and prove it there. And someday, if it works, move it into space. And that's all I have, and thank you for your attention.